Hello and welcome. In today's video, we will discuss about searching, inserting, deleting, and finding min-max values in a binary search tree. Searching for a value in BST is very similar to binary search algorithm, how we find a value using binary search technique in an array. For binary search to work, first thing we need is the array must be sorted already, and searching for a value in an array can be done really very fast. Similarly, searching for a value in BST can also be done really fast because of the nodes are placed in such a way the parent's left is always lesser and parent's right is always higher. Let's look at a sample binary tree diagram. So we have root 39, it has children 7, 15 and the following children, and this is a sample binary tree. So let's start with searching for a particular value. How basically we will search for a value in this binary search tree? We need to start with the node. If the value is this value of a root, then return it is found. And if the value is higher and traverse to right, if the value is lower than 13, and then we will have to traverse to left. Likewise, we will follow the same step. We will check whether the value is matching with this. If it is matching, we will return the value found. If it is not matching, we will check whether the search value is lesser than 7 and navigate here. If it is greater than 7, navigate here and check the condition whether the value matches and return if it matches with either of them. So that is overall process of searching. Let's now look at the programming logic by debugging. So in previous video, we have seen how to traverse through a binary search tree. Let's now look at the code for the similar but for searching. So this is the method. So we have method already created here for searching a value in the binary search tree. So let's now we are having 13, 7, 15, 3, 8, 14, 19 and 18 as in this diagram. So let's run set the pointers, debug pointers before actually executing the script. Let me comment out this code. Just execute for search and see how it works. And so for this is a script called BST. Let me open the actual file. Okay, so this has only search. So now we see this has only search logic. We have set the debug pointers already. So it has to search for the element that we have specified in search, and we are passing root node to the search method. So it will have to find the value 13 from the tree just we have seen. Let me start debugging. How can I debug? By selecting Python debugger. So the debugger has started and it came to this step because I have set a debugger point here. So it created all the above nodes. You can see here, and let me pass this step. So node 19 is also created. Now it calls search method. So node is root 13 and the target we have to find is 13. Now it is checking if node is none. Node is nothing but root that is none. It is false. So it has gone to else if node dot data equal to 13. So node dot data is 13 and target is also 13. So now it has to return that node. So it returned node and it got stored into result. Let's see what is the value. So it has the value of root 13. So it will print now found the node with value data. So it printed found the node with value 13. So the execution has stopped because that is the end of the program. And now if you want to search any other element, as we are searching for the element which is root already, it has found in the first place. If you are trying to find something like 8 or 18, it will traverse through other steps in the search. Let's try with we will try with 8 and 14 and one non-existent element. Let's try to find first 8. So let's see. Let's start the debugging. It has created all the nodes. It's calling a rooted target as 8. It is not none, so it goes to else if. So node dot data is here 13. Target is 18. Sorry, 8. So it compares 13 equal to 8. False. So it has to go to else if. And here checks target 8 less than node dot data 13. 8 less than 13. It is true. So it goes and return. Search it again calls node dot left. Because it is lesser, it has to go to left. Because all the values that are lesser than 13 are inside left. So node dot left is 7 and then target we are passing 7 and 8 to search in recursive manner. So now node has become 7 and target has become 8. It is not none, and 7 equal to 8, false, and 7 less than, sorry, 8 less than 7, false. So it goes to else, and it again calls search node dot write. So 7's write is 8. It will pass 8 and target 8. So it checks. It is none, not none. Node dot data 8 is 8 and target is 8. It checks 8 equal to 8, which is true. So it returns node and assigns to result. So result becomes 8. So it will print found 8 and the execution ends. So if you try to find a non-existent element, let's say 100, let's start debugging. It created all elements. Calls search with 13 and 100 target. It is not none. It is not equal to, target is not lesser than 13. So it calls write and we have passed right, which is 15 and target 100, not none. 15 not 100. 100 is not less than 15. So again moves to right. 15's right, which is 19. 19 and 100 is not equal to, or 100 is not less than 19. So again it tries to send right, which is none for 9. There is no right node. There is no right node and there is no 100 as well. So it is now node is none and target is 100. Now it checks for node is none and it is true, so return none. Because the element is not found, it returns none and result becomes none. If result, because result is having value none, it becomes false and goes to else and prints value not found in the BS tree. So that is the output for 100. Because it is not available, it prints value not found in the binary search tree. So if we look at the time complexity for searching a binary search tree, for the value it is O of h, where h is the height of the tree. And for binary search tree with most nodes on the right side, for example, the height of the tree becomes larger than it needs to be and the worst case search will be longer. Such trees are often called as unbalanced tree. Let us look at an unbalanced tree example. We have an unbalanced tree which has right exterior children, so like this. So its height is growing because of its alignment like this. This is called as unbalanced tree. Searching element and finding it inside unbalanced binary search tree is little bit time consuming because its height is larger than as expected. So in order to traverse any of balanced or unbalanced, it gives the same result, but as its height is different, the time consumption is varying. And if you want to create a binary search tree like this, we have a code. This is the code to create that particular unbalanced tree. So you can start creating nodes for this. We can take the binary search tree node from here, and if you execute, it will create this unbalanced tree. Let me execute the unbalanced tree creation. It will create. So if you see here, root is 7, like here, root is 7 and its children. So let me pass this. It has to execute to assign the left and right. So it has assign and left and right. So for 7, 7 is root and it has left 3, right 13, as we have in our diagram 3 and 13. For 13 it has to be 8 and 19. So we have not assigned. We can write for node 3. Let me write. So we have for 3 there is nothing. 13 it is there. So whatever it was there, that was accurate. So for 3 there are no children. For left there is no children. For 13 it has left is 8 and right is 19. And for 19 we have left as 14, 19 we have left as 14 and 14 has right 15 and 15 has left which is 18. So that's the last child. That's it. This is how we create unbalanced tree, and even I can write the same search and do a search in the unbalanced tree as well. Only difference is it will take more time because of the larger height. We have seen balanced and unbalanced trees and how to traverse and search a node. Now let's see how to insert a node. We have created an example for inserting a node. Search is not required. So we have insert method here is doing certain logic. Let's go through it and debug it, debug it further to understand how insert happens in the binary search tree. Before that, let's understand how insertion of a node in BST works. First and foremost step for BST is for any operation start at the root node. As we have in the diagram also, we have start with root node and compare each node. Is the value lower, go left. Is the value higher, go right. And continue comparing nodes with the new value until there is no right or left to compare with. That is where the new node is to be inserted. So for example, we have to insert 5 to this particular unbalanced tree. So we will check. We'll start with root 7 and compare 5 less than 7. So go left. 5 greater than 3. So go right and add it in the right side. So we can add add 5 in right side of this particular element. So that is how steps logically we will insert a node to the unbalanced tree. And we have to note one point that all the nodes in the BST are unique. So in a case of if we find the same value as the one we have to insert, we do nothing because it is already present in the BST. Let's now go to the insert method and try to execute it and insert one node here. So we have this particular balanced tree. So let me go back to our balanced BST binary search tree, which is this one, and we have written code for the same. These all steps will execute and create nodes and create a BST. So now we can remove the insert search logic. We can uncomment. We can uncomment both. Insert and delete, and let's see how the for min also we will set. Let's set for insert also. We have to see the execution step by step to understand the logic. And for find, and we have to set debugger point for max, and we will set the same way for deletion also. As we have so many steps in delete, we can just set for the condition check. Finally, return. So let's start the debugging by clicking Python debugger, debug Python file. So first, it will have to create all the nodes. It is throwing some name error. Name error. Search is not defined. So we are trying to search for this, but search method is not available as we have removed. So what we will do, we will remove this particular call because we have to only see now the insert. So now it has created all the nodes with root 13. Let's see. So this has been executing the previous script. We are actually trying to execute the newly created insert script. Let me find. I have only insert, and we just stop this one. At least if you can see, okay. Now it got stopped. We need to debug this particular script for insert. So it has created root 13 and its children. Let's in the next step we have called insert. We have passed node as 13, which is root, and key, the value to insert is 10. So node 13 is not none. It has to go to else, and then key 10 less than 13, true. So node dot left equal to insert node dot left key. So again node dot left, which is 7, 7 and 10, key is 10, will be passed to insert in recursive manner. If you see, node became 7 and the key is 10, not none, and 10 is less than 7, false. So it went to else condition and calling insert node dot write. So this node dot write 8 and key is 10. So that will be passed to insert again 10 and 8 if you see, and it is checking none, not none. 10 is less than 8, false. So again it will call node dot write, which is none, none and 10. If you see here, none and 10, the node is none, true. So return TreeNode of key So we are creating TreeNode of creating here 10. It is, and then return node which is 8. It goes back to 7. It goes back to 13, and the node 10 must have been linked as required. So if we can try to see for node 10, actually it is not available here. It must be present. So after this, if you observe here, it has gone to this particular statement, and for node 8, it has added in the right the target insert value. So as we have this particular balanced tree, the node 10 has been added here. So like this, we have inserted from this insert method. So to the node 8, it got added at right side. Somehow the tree node that we have created is not visible here. Maybe we can check in globals. It must be available. Somehow it is not visible. Let's pass this step and see if it is showing node 10. Okay. Node 10 is not visible as part of the variable, but it is linked and created inside the tree. So now we are in find min. Node value is 13, which is root, and we are trying to find minimum. So current node becomes node which is root, while current and current dot left, current is 13, current dot left, 13 left is 7. We are passing current and current dot left. For while statement, we are checking whether both of them existing as 13 and 13, current equal to current dot left, and current becomes current dot left, which is 7. So you can see current became 7. Now current dot left became 3. So when it is 3, current is 3 and 3 is left is none, so it fails, and while loop stops, and the value 3, which is current, will be returning. So current value 3, which is minimum. It is just going to the extreme right, left, and showing the minimum value among the tree. Now find maximum. Again the same. What we are checking. Previously we checked current dot left, and now we have to find maximum. So we have changed it to right and returning the current at the end. If you see, it goes to extreme right. Now it is 19 as 19 has no right. It gets min and maximum. So minimum is 3, maximum is 19. That's how min max value can be found in BST. Now let's walk through delete node. Here we are trying to delete node 15. So this node must be deleted and this has to be arranged in sorted order. Let's see how this works. So key we have passed 15 and root is 13 as it was 13. If root is none, false. If key which is 15 less than 13, false. Key greater than 13, true. Root dot right equal to, again we are calling delete node with root dot right. Root dot right is 15 and 15. So now 15 is none, false. 15 is less than 15, false. 15 greater than 15, false. It goes to else and checks. Root dot left is none, means 15's left is none. False. It checks else if right is none, that is also false. So now what it does, before deleting it, it has to link its children and place them in order. So find min of root dot right. So now root is 15, root dot right. We have to, root dot right is 19. We are passing to find min, means we are trying to find for the tree with 19 as root, which is minimum. So in this case it is 15. This has to be returned. So after execution, temp becomes 18. You see, it is 18. And it altered those left and right. Deleted node with value 15. It prints deleted node. If you see in the logic for delete node, what it does, it finds temp, find minimum becomes, in this particular diagram, with 19 it is 18. So temp becomes 18, and then root dot data equal to 18. and root dot right equal to delete node root dot right, which is in our case 18's right, which is none, and temp dot data is 18. So it changes. Basically, what it does, it places 18 in place of 15, and 18's right becomes 19. That is what it is happening here. Root dot right equal to delete node root dot right temp data. So we are linking. If we are passing to it, it will return 19. So 18 side becomes 19. So that's how it deletes 15 and prints it got deleted. So that's about deleting records from binary search tree. And we have seen min and maximum value from binary search tree as well. So you can try to execute it as many times for your better understanding, and let us know if you have any doubts and any clarification required in the comment section. Thank you for watching.